Welcome to SS2 Further Mathematics, Term 3, Week 10. Linear programming is an optimization technique. It finds the maximum or minimum value of a linear function subject to a set of linear constraints, inequalities. It is widely used in business, manufacturing, logistics, and resource allocation. By the end of this lesson, you will formulate linear programming problems from word problems, identify feasible regions using linear inequalities, find optimal solutions using the graphical method, and answer WAEC further mathematics questions. Let us begin. A linear programming problem consists of decision variables, the quantities we want to determine, e.g. number of units of product A and product B to manufacture. Objective function, what we want to maximize or minimize, usually profit or cost, a linear expression in the decision variables. Constraints, limitations, e.g. available materials, machine hours, labor, expressed as linear inequalities. Non-negativity constraints, all variables greater than or equal to 0, we cannot produce negative quantities. Standard form of LP, maximize Z equals X plus by subject to L1x plus M1y less than or equal to N1, L2x plus M2y less than or equal to N2. Inequality constraints, x greater than or equal to 0, y greater than or equal to 0. Worked example, a carpenter makes chairs, C, and tables, T. Each chair requires 2 hours of labor and 3 m of wood. Each table requires 4 hours of labor and 5 m of wood. Available, 80 labor hours and 120 m of wood per day. Profit, N 3,000 per chair, N 5,000 per table. Maximize profit. Decision variables, C equals number of chairs, T equals number of tables. Objective function, maximize Z equals 3,000 C plus 5,000 T. Constraints, labor, 2C plus 40 less than or equal to 80. Wood, 3C plus 5T less than or equal to 120. Non-negativity, C greater than or equal to 0, T greater than or equal to 0. The graphical method works for 2 decision variables. Steps. Step 1, graph each constraint boundary, convert inequality to equation, draw line. For 2C plus 4T equals 80, when T equals 0, C equals 40, when C equals 0, T equals 20. For 3C plus 5T equals 120, when T equals 0, C equals 40, when C equals 0, T equals 24. Step 2, determine which side of each boundary satisfies the inequality. Test the origin 0, 0 to 0, plus 4 or 0 equals 0 less than or equal to 80, origin is in the feasible region for the first constraint. Step 3, the feasible region is the set of all points satisfying all constraints simultaneously. For the example, shade the region below / left of both constraint lines and in the first quadrant, C greater than or equal to 0, T greater than or equal to 0. Step 4, find the corner points, vertices, of the feasible region. These are the intersections of the constraint boundaries and the axis. Corner points, 0, 0, 40, 0, intersection of 2C plus 40 equals 80 and 3C plus 5T equals 120. Solve, from first, C equals 40, 2T, substitute, 3, 40, 2T, plus 5T equals 120 120 minus 60 plus 5T is equal to 120, T equals 0 T equals 0, C equals 40. This gives the same point, 40, 0. Try 0, 20 check 3, 0, plus 5, 20, equals 100 less than or equal to 120, feasible. And 0, 24 check 2, 0, plus 4, 24, equals 96 greater than 80, not feasible. Finding the actual intersection, solve 2C plus 40 equals 80 and 3C plus 5T equals 120 simultaneously. 2C plus 40 equals 80 multiplied by 3, 6C plus 12T equals 240, 3C plus 5T equals 120 multiplied by 2, 6C plus 10T equals 240. Subtract, 2t equals 0, t equals 0, c equals 40. Feasible corner points, 0, 0, 40, 0, 0, 20. Wait, need to check all intersections more carefully. The corner points of the feasible region are the vertices where two boundary lines or axes meet. Here, 0, 0, 40, 0, intersection of 2c plus 40 equals 80 and 3c plus 5t equals 120 equals 40, 0, from above, they intersect at the axis, and 0, 20. Corner points, 0, 0, 40, 0, 20, 10. Actually, let me read you. 2c plus 40 equals 80, divide by 2c plus 2t equals 40, 3c plus 5t equals 120. From c plus 2t equals 40, c equals 40, 2t. Substitute, 3, 40, 2t, plus 5t equals 120, 120 minus 60 plus 5t is equal to 120, t equals 0, t equals 0. So they intersect on the c-axis. The feasible region has corners at 0, 0, 40, 0, and 0, 20, with 0, 20 checked feasible. Step 5. Evaluate objective function at each corner. Z 0, 0 equals 0, Z 40, 0 equals 3000, 40 plus 5000, 0 equals 120,000, Z 0, 20 equals 3000, 0 plus 5000, 20 equals 100,000. Maximum profit equals N120, 000 at C equals 40, T equals 0. Corner point theorem, fundamental theorem of linear programming. If a linear programming problem has a bounded feasible region, the objective function attains its maximum and minimum at one of the corner points, vertices, of the feasible region. Why? The objective function z equals x plus by is a linear function. Its graph is a family of parallel lines for different z values. As we move these parallel lines in the direction of increasing z, for maximization, the last corner point of the feasible region touch gives the maximum. Algorithm: enumerate all corner points, evaluate z at each, choose the corner point giving the highest z for maximization, or lowest z for minimization. Special cases: if two adjacent corner points both give the maximum z, then every point on the edge between them also gives the maximum, multiple optimal solutions. If the feasible region is unbounded, the maximum may be infinite, check carefully. If the constraints are inconsistent, no feasible region, there is no solution. Standard WAEC further mathematics approach: draw and shade each constraint, identify corners of feasible region, shaded area, solve pairs of equations to find intersection coordinates, evaluate z at each corner, state optimal solution. Worked example 2, minimization. A student is planning meals, sandwiches, S, and salads, L. Each sandwich provides 400 kilocalories and 10 g protein, each salad provides 200 kilocalories and 20 g protein. She needs at least 1,200 kilocalories and at least 50 g protein daily. A sandwich costs N500 and a salad costs N600. Minimize cost. Variables: S, sandwiches, L, salads, S greater than or equal to 0, L greater than or equal to 0. Constraints: 400 S plus 200 L greater than or equal to 1,200, simplify, 2s plus L greater than or equal to 6, 10s plus 20 L greater than or equal to 50, simplify, s plus 2L greater than or equal to 5. Objective: minimize z equals 500 s plus 600 L. Graph: 2s plus L equals 6, points, 3, 0, and 0, 6. S plus 2L equals 5, points, 5, 0, and 0, 2.5. Feasible region, above both lines, greater than or equal to constraints, first quadrant. Corner points, intersection of 2s plus L equals 6 and s plus 2L equals 5, from first, L equals 6, 2s, sub, s plus 2, 6, 2s equals 5s plus 12 minus 4s is equal to 5-3s equals minus 7s equals 7/3 is almost equal to 2.33, L equals 6, 14/3 equals 4/3 is almost equal to 1.33. Other corners, 5, 0, check 2, 5, plus 0 is equal to 10 greater than or equal to 6, 0, 6, check 0 plus 12 is equal to 12 greater than or equal to 5. Evaluate z, 5, 0, equals 2,500, z, 0, 6 equals 3,600, z, 7/3, 4/3, equals 500, 7/3, plus 600, 4/3, equals 3,500 divided by 3 plus 800 is equal to 1,166.67 plus 800 is equal to 1966.67. Minimum is at 7/3, 4/3, but this is not an integer solution. Integer programming, if the decision variables must be integers, round to nearby integer solutions and check feasibility and objective value. Here, try 2 plus 2 equals 6 greater than or equal to 6, 2 plus 2 equals 6 greater than or equal to 5. Z equals 1000 plus 1200 is equal to 2200. Try 3, 6 plus 1 is equal to 7 greater than or equal to 6, 3 plus 2 is equal to 5 greater than or equal to 5. Z equals 1500 plus 600 is equal to 2100. 3, 1, gives lower cost and is feasible. Key points: linear programming, maximize or minimize a linear objective function subject to linear inequality constraints and non-negativity. Steps: identify decision variables, write objective function, write constraints as inequalities, graph each constraint, identify feasible region, intersection of all constraint half-planes, find corner points, vertices, evaluate objective function at each corner. Optimal solution is at the corner given marks, or min, z, corner point theorem. Optimal value occurs at a vertex of the feasible region. Maximization, move objective function lines in direction of increasing z. Minimization, move in direction of decreasing z. Unbounded regions, check whether maximum/minimum exist. Multiple solutions, if two adjacent vertices both optimal, the entire edge is optimal. WAEC exam style, formulate the LP problem from a word problem, draw and shade the feasible region, clearly mark corner points, show evaluation of z at each corner, state optimal solution with values of all variables.